Hi, it's Mr. Anderson, and in this podcast I'm going to talk about the sensory system. Sensory system is basically how you sense information in your surroundings and then transfer that to your brain. And you're using a number of senses right now. You hear me, and you can see me, and you can't smell me, but you might be able to smell something around you. And so basically, the cool thing about it is what goes to your brain are simply nerve signals, or we call those action potentials. But what your brain does with it is way more complex with that. I can't even get into that today. And what do I mean by that? Well, right here we've got this cylinder and A and B, and A and B, this is just an optical illusion, are exactly the same color. In other words, they're the same hue of gray. And you might say, no way, if I were to remove the rest of the drawing, then you see that they're the same color of gray. And so even though when they were together, let's move it back again, even though they're the same color of gray, and your eye is receiving that color of gray, your brain is making sense of it. And it's doing that because it realizes this is maybe in a shadow. And so even though the sensory system brings action potentials to your brain, know this, that your brain can do a lot with it when it eventually gets there. And so review a little bit of the nervous system. Basically, nerve signals are action potentials. So basically, all the nerves are sitting at negative 70 millivolts. Anything that pushes it towards that can cause an action potential. Action potential goes up, we have an undershoot, and eventually goes back to negative 70. Now, what's causing that is going to be sodium and potassium ion flow. But basically, what it looks like to the brain is an action potential and another action potential and another action potential, and another action potential. And all the action potentials are identical in size and identical in shape. But your brain is receiving those, and it can tell what the signal is based on where the signal's coming from, what nerves it's coming from, and basically the number of action potentials you get. And so if I were to make a noise like, ooh, then you'd be getting action potentials from your ear, and a set number of action potentials because it's not really loud and it's a specific pitch. But if I were to make a slightly louder noise, whoa, like that, then that's going to be way more action potentials. The first sound we could think of as like this, but the second one, it's going to be way more action potentials. They're always the same size, but more action potentials in a given period of time. And so again, the action potentials from your nose and the action potentials from your eyes and your ears and all of those are exactly the same. They look exactly the same. You either have more of them or less of them. And so you might think to yourself, well, how many senses do you have? Most people would say 5. We have 5 senses, and then we have a 6th sense, which is not something that I'm even going to talk about. But basically, that would be way underestimating the number of senses. Because you can see, you can hear, you can taste, you can smell, you can touch, but you also have a sense of balance. You make sure that you're remaining upright. You can sense temperature. You can sense pain. You can sense acceleration. You have kinesthetic sense. I mean, take your finger. Close your eyes. Can you get your finger to your nose? Yeah. How are you doing that? Well, that's kinesthetics. And then you have dozens of other senses inside our body, internal senses. And so if somebody says, we've got 5 senses, I know I'm being picky here, but we have way more. We have about 25 senses. Today, what am I going to talk about? Well, I just want to talk about 3 of those. I'm going to start with the smell. Smell's not super important in us, but it is important. But just as an example for the next 2, which are going to be vision and then hearing. And so basically, how does smell work? Well, this is your nose right here. So you have this olfactory bulb, which is right up at the top. So we've kind of zoomed into it here. And so if you want to smell something, how does that work? Well, if you really want to smell a rose, then you kind of sniff because you want to bring those chemicals up into your nose because this is a chemical sensor. Just like your taste buds are sensing chemicals that end up on your taste buds, your sense of smell is the same way. So the more of those you can get up to this point, the better our sense of smell is. And a dog is going to have way more receptors than we do. But basically what happens is those odors are eventually going to dock with these olfactory neurons right here in your nose. And every time they interact, they're going to cause interactions. And so the more interactions there are, the more action potentials are going to be sent to your brain. And your brain is going to sense that, and they're going to be able to tell you what that smell is, or more of that smell. Now, if you've ever walked into somebody's house, you'll notice that their house smells different than your house. They have a smelly house. But then the longer you're there, eventually you're going to ignore that. And so even though those smells are present, our brain can decide what we want to do with that as well. But what's going to your brain? Again, it's just action potentials that are being sent down the neurons that go into your brain. And if those action potentials aren't present, then you're not going to be able to smell it. But you're sensing a chemical smell. Let's go to the next one, which is vision. How does vision work? Well, vision, basically you have a pupil up here, you have an opening, we have a lens that we can change the focus of. But let's see, if I were to draw something out here, let's say you're looking at a person that's far away. Basically that light is going to be bent. So it's going to be bent like that. And it's going to be projected on the back of your eye. And so again, if it's that's a really bad drawing, but basically we can regulate the amount of light that gets in, but this ends up on the back of our eye. We're then going to transfer that into action potentials that go to your brain. So your brain is going to flip that image right side up. But how does that work? How do we sense that on the back of our eye? Well, basically on the back of our eye, you learn this as a kid, we have rods and cones. And so rods and cones are going to be found here. Cones will be closer to the middle because cones are good at sensing. We have what are called this fovea, where there's this area where we have lots of cones, we can sense lots of color. And then as we move farther out, we're going to have rods, which are going to sense low light conditions, but they're going to be in black and white. But what do these receptors look like? Well, this is one right here. This would be a rod right here. Rod's going to pick up light. So basically down here, it's just like a neuron, but we've got a sensory portion to it. You can see that there's a synapse here, and then that's going to send that to cells that will go through the optic nerve and eventually to the brain. If we zoom in right here to this area, we get a lipid bilayer, and then we have a chemical called rhodopsin. Rhodopsin is going to pick up light. And so when light hits that, so when light hits rhodopsin, what's going to happen is it's going to have a conformational change in the protein. The protein will actually change shape. The rhodopsin is going to change its conformation. When it changes its shape, that's going to send an action potential down here. It's going to send an action potential down a nerve, and it's going to eventually go to your brain. And so when you see light, so if we see light here, more light on this side of the retina, that means more of the rhodopsin is changing its shape, and we're sending more of a signal. Likewise, if we see a dark area, or even if we were to close our eyes, we're going to have all that rhodopsin go back to a specific conformation. We're not going to send action potentials to the brain. You've noticed this sometimes. You're in a theater, it's really, really dark. You forget that you're in a theater during the day. You go outside, bam, and you get that light. Well, that's basically all of the rhodopsin and all the rods that are being bleached. We call that. They're sending a bunch of action potentials right to your brain. And so that's the way vision works. And vision is super important in us. And so we have tons and tons of receptors, tons and tons of these neurons that are going to send information back to the brain because we're visual kind of people. Hearing is another one. Hearing is not using electromagnetic radiation. Hearing is actually using compressional sound waves that are passed in through the air. And so basically when I talk right now, I'm vibrating the air, and that vibrated air is moving into your ear. It's going to vibrate this. This is called your eardrum. We have a series of bones which are going to mechanically amplify that until it eventually gets right here, and this is going to be your oval window. So the oval window sits right here on your cochlea. The cochlea looks kind of like a snail, and that's where you sense hearing. On top of that, we have these semicircular canals. Those are actually going to give you a sense of balance. And so there's fluid inside here, and they've got 3 different dimensions. And so basically you can sense movement through 3-dimensional space. But how do we sense sound? Well, this is an awful drawing here, but basically if I were to take the cochlea and unwind it, what you get is this long tube. And so basically the fluid in here is going to vibrate. There are going to be nerves that go out of here to the auditory nerve. So again, I've unwound the cochlea. So basically what happens is you're going to vibrate the fluid inside the cochlea. And depending on the pitch, you're going to vibrate it in a different area. Example, a whale's cochlea is going to be really, really big, And so it's going to be able to sense really low frequency sounds that we couldn't even pick up. If we had something like a dog that can hear high frequency sounds, it just means that their cochlea is going to have more neurons, and it's going to have a smaller area in there. Because when we vibrate the sound, we're going to vibrate a specific portion of that cochlea, and that's going to send a signal down to our brain. Again, we're going to sense it. It's just going to be action potentials coming to the brain, but since it's going to that portion of the brain where we sense hearing, we're going to hear that as a sound. And sometimes those get crossed. You'll have people that can actually, they'll hear sounds and it'll be like a color, or they'll smell something and they'll see a color. And so it's basically action potentials going to the wrong part of your brain. But that's the sensory system, and I hope that's helpful.